We'll start with the design of CLT diaphragm in X direction. Here we have additional input needed for the design. So we have both factorized loads for ultimate and serviceability limit state loads, because we have both strength and serviceability checks. And also we use Eurocode screws for this connection, since we were considered slip modules within the calculation of the diaphragm. So let's jump to the app and start with the design. So the first, in our recent update, as Ringo mentioned in the beginning, we launched a community forum inbuilt into the app. So this is on the left. So if you want, if you have any questions related to the calculators in the app or in general with mass timber, feel free to join the conversation. Regarding our calculation, we can start with CLT diaphragms. So we'll create a new project on the company level. I'll type in, so webinar 2, and we can calculate CLT diaphragm, something like this, and we'll create this calculation. So at the beginning, we can set up what we have, either a manual input or a custom supplier, or some of the available suppliers that are we have already partnered with. So as we designed in the previous session, we'll start with we input the KLH 5 layers, 180 millimeters. Also important to know that this calculator is only available to Pro and Enterprise users. So on the right image, we have dynamic image of the preview of the geometry, connections, panel connections, and total of factorized force for ultimate and serviceability limit state. And below we have stored input, so similar to other calculators we have. So at the beginning, we can set up geometry first. So we can type in 24 by 12 meters. So we're going to take only one diaphragm, as we explained at the beginning. Or for the panel-to-panel connections, we can select a half-lap joint. Also, we'll configure the panel orientation to Y direction and also orientation to vertical. So we'll match the orientation from the diaphragm and the forces that are applied to this specific scenario. Also, what is important, we'll type in the panel width, so 2.67 meters as we have listed, and also we can set up spacing as 150 millimeters. Also, what is interesting about the panel width and how you can start with selecting the proper dimension. You can always use more information from each supplier, and you have some technical about, besides some information about supplier, you have technical information where you can find maximum panel width and production, also for the production and transportation limits. So you can use this as a starting point for picking the right width of your panel. For the connection data, we'll use supplier specific, but also there is ability that you can use user-defined values or strictly Eurocode, or pick up the right supplier. So based on the appropriate producer, family, and exact type and diameter of screw, it will be included into the app. So for example, we can start with panel twistic 6 times 160. And going further, we have option for selecting design. So this is set to Eurocode, ProHoltz, and ambient case. We'll leave all the inputs as they are. For the input forces, we have lateral deformation in Y direction that is set up properly. And also we'll type in the proper values that we have inputs with. So I'll type in for ULS 11.39, and for the serviceability limit state load, we'll type in 7.59. For the in-plane shear values input, so these inputs are left as a user input because they're not described for each supplier. So they are based on some recommendation from design guidebooks and other research papers, but you can find some specific with each supplier. So for instance, for the KLH, we can type in 5.2 for shear net strength. So also in terms of the lamination data, this is also part of the inputs that are specific to supplier, and you can find more information in their technical data. So for the transfer lamellas, in this case, we'll type in 80 millimeters, and for the longitudinal, we'll type in 120. Going further, we have the last part of the inputs regarding the design data for Eurocode 5. So we have cases, gamma, we have option for deflection ratio, also a shear correction factor that is depending on the geometry and aspect ratio. Also, the key mode will change this to 0.9 because we have wind governing in our load combination, and we'll leave the service class to 1. For concerning the output summary, we have a preview of in-plane deflection, bending, shear, and in-plane tensile stress. We can see that the thickness of the panel is not governing, but we're going to go through these results in detail and see all the specifics and how we can use some of these results for calculating the connections. So going first into panel properties, we have information about the panels and the stiffness calculation for the in-plane deflection. So as mentioned at the beginning, we have here CLT diaphragm based on the substitute deep beam analogy. So it's based on the Pro-Holtz method that we described at the beginning. Also, we have here information about the stiffness of the connection and how this is being calculated into the total stiffness. Also, based on the research papers we explained, we have information about the total and formulas listed for the total deflection. In this tabulated format, you can see step-by-step calculation, and in the end, we have information about the midspan, deformation of the diaphragm, and total stiffness of the diaphragm. Also, below we have information about the contribution of the connection to the overall stiffness and the advanced things that you can use for serviceability verification, and also compare with other tools. For going further, we have information in the actions. So we have here shear and bending moments actions in this tab. And in this strain tab, first we have information on the verification of the CLT diaphragm starting from in-plane bending design. And in this part, we have also determination of the joint forces from plane effect. And we can stop here for a minute just to see how we can use some of these values for our connection design. So we have here locations of each joint that we have in our diaphragm. So we have 9 axes, what is presenting 9 connections or axes of connections. We have location of each joint, and for each joint we have information about the shear forces, or even short force field fastener moment, but also axial forces. So we can use these values for determining and optimizing the connections in our panel-to-panel connection design. So we'll use 8x86 and 6x76 for the panel-to-panel connection. Forces are highest at the end, but this can be used for panel-to-beam connection. While we'll design panel-to-panel connection, we're going to use this one. Also, going further, we have information for further optimization on the panel design, tension and compression strain information, in-plane shear design, including all three mechanism types, also from Pro-Holtz design guidebook. So going further, we'll take some of the information from the panel-to-panel connection from this diaphragm calculator as inputs for the next calculation. We can go quickly on the top. We'll click Save.